Today I want to talk about gradient descent. It is one of the most widely used methods in optimization nowadays. And I want to talk about two parts. It's an extremely fast forward version of at least several lectures in an optimization course. Okay, so it'll be extremely high speed. And then I will skip a lot of proofs, but I will draw many pictures to make sure that you get the insight, so that if you have a chance to take another optimization course, you know what they're doing. So that's the purpose of today. Now, if you look at the diagram here, you see that we are sort of towards the end of the first part of our course. The first part of our course is a light speed journey through this pipeline of machine learning. So in these 5 lectures, we actually go through all the necessary steps that you will encounter in a machine learning method that involves feature extraction, that involves finding the model, setting up the loss, and then solving the problem using optimization algorithms. Okay? Now, in the later part of our course, you will have many opportunities to see these blocks again and again. So if you're not getting the whole idea yet, it's okay, because we will revisit them. So if you have any questions, okay, something that you're not too clear yet, just bear with me, because it will take some time, because you're trying to figure out this entire big subject, and then we need to do it slowly, okay? So now we're covering one part. The first part is to cover the entire picture, just like a very quick scan through of all the essential components. And then part 2, part 3, part 4 of the course, we will start to get a better and better idea of what all these components are. Okay, so now we're at the end of this general pipeline. We want to talk about optimization method. And as I said, I want to talk about gradient descent because of the popularity nowadays. So I want to talk about 2 things. Gradient descent is picture. And then I want to talk about stochastic gradient descent and its picture. Okay? Now, gradient descent, it is the basis of stochastic gradient descent. And stochastic gradient descent is actually what you use in today's deep neural network algorithms. So whenever you download a TensorFlow, you download a PyTorch, you start to type something, and then you use Atom Optimizer, you are doing things according to stochastic gradient descent. So we want to understand at least pictorially what they are. Okay, so let's talk about gradient descent, and let's talk about its goal. Okay, so the problem is very simple. The problem is that you have a function, g theta. This is your loss function. Okay, so if you go back to a few lectures, when we talk about this loss function, okay, so there's a loss function here. The loss function, it captures your prediction and also the true label. Okay, so prediction, you dump in an image, and then the predictor will give you a label. That's the predicted label, and then you compare with the ground truth label, and you're not happy, and so you send the residue back to the optimization algorithm and try to minimize. Minimize what? Well, by finding a better model, by finding a better predictor. Okay, so that your prediction becomes better. And so what do I mean by a better predictor? Well, of course, there's a parameter, the parameter theta that controls your predictor. Okay, so you have a loss function here, is parameterized by this theta, and you want to find a good theta that can minimize this loss function. Now, there are multiple ways of solving this problem depending on what loss function we have. If we have a least squares, if we have a linear regression type of loss, we know that there is a closed form expression, and we have done some study there. But in general, you have a lot of complicated problems, and that cannot be solved easily by just writing down the equations. And so we need algorithms. This gradient descent, it is one of the easiest algorithm that you can derive. And now, the following equation, it is a description of this gradient descent algorithm. So I'm going to switch my notation from theta to x, just to match the textbook notations. So imagine that you have a point x, and then you are currently at iteration t. Okay, so now it is an iterative algorithm. Your iteration t. You take the current point, and then you subtract something, and then you're going to define the new point. Okay, so let's look at the picture here. So you are currently at x1, so this is your current estimate, and then you're not happy about this current estimate because your objective value is not minimized, the loss function is not minimized, so you want to make some move around yourself, okay? So you want to find a good search direction, and then make a step to x2. Hopefully at x2, you have a lower loss function value. So that's the goal, okay? And then hopefully by doing x3, x4, eventually you can get to a point that has the minimum cost value. So that's the gradient descent algorithm. But why is it called a gradient descent? Of course, there should be the gradient involved. Where's the gradient? What gradient is this? Okay, so let's say you have a function f, and then you plug in this number x of t into the function, and then you evaluate the gradient. So that's called a gradient. And then you put the alpha t. Alpha is called the step size, okay, which I'm going to talk about that later. So what does this mean? Well, you have x of t, and then you find out a good search direction. So this is called the search direction, okay? So now you have a search direction delta f, and then you make a step according to the step size alpha, and then you go to x of 2. Okay, and then when you x of 2, you replace this x of t by x of 2, and then you make another step, another step, another step. So gradually you can go into the minimum point. That's the hope. Alright, so that is the idea of gradient descent. Now, there are a couple questions here. The number one question is, why do we want to choose the search direction as the gradient? Okay, there's so many search directions to choose. I can choose here, there, but why do you want to choose the gradient? It appears very magical, okay, if you don't really look at the optimization literature. Whenever people talk about gradient descent, take a gradient, go to there, it sounds very magical, right? So now, it's not that magical if you go back one lecture, okay? So we call it in lecture 4, when we define optimality, x star, we actually showed that the first order condition has to satisfy this, where you take a gradient on f, you evaluate x star, you take the inner product with any d is a search direction, it has to be positive. Okay? Now, this is true when your x star is optimum. Now, when your x star is not optimum, that means you can always find at least one d, okay, at least one d, such that this becomes negative. Alright, so that goes to the second point. If xt is not optimum, then what do we want? Well, so let's look at this equation. You have f on both sides, and then on the left-hand side, you are evaluating x at t plus epsilon times d. That means you are currently x of t, and then you want to find a good search direction with certain step size epsilon. Hopefully, when you go there, you evaluate your point, well, then you have a lower cost value than you're currently at. If you can find that, great, because then you can just walk that step, and then you will reduce your loss function value. Okay, so now if you want this to happen, then that means you want this gradient of f transpose d to be negative for some d, okay? At least for some d, now not all d, okay? For some d, you want it to be a negative. So what does it mean? Well, it means the following picture. Suppose you have all these contours, they're defining the sets, okay? And then out of the contour, you have a higher cost value. Now, imagine that currently you are at this point. Okay, and then as I showed you last time, when you draw a gradient, let's imagine that it's pointing outward. Okay, let's imagine it's pointing outward. So this is the normal direction, and then there is a tangent line. That's your tangent line. Okay, now if it is optimum, then we know that this gradient has to be 0. But if it is not zero, then that means you can always find a few red arrows on the left-hand side of this plot. Okay, so that when you take the inner product of your red arrow with this gradient, it will be negative. See the point? Okay, so if you can find that, then I ask you, what would be a good search direction? Well, actually any direction that is on the left-hand side of this tangent line would be the good search direction. Okay, who say that it has to be negative gradient? No one has said that, okay? As long as you travel on towards the left-hand side of this half plane, you can guarantee to reduce your cost value for an appropriate choice of epsilon, right? Now, of course, if you say that, okay, I want to travel along here, if my epsilon is extremely big, my step size is extremely big, of course you will overshoot, okay? But assume that you can, for every search direction, you can also search for the best possible step size. Then this is a legitimate, it is an allowable search direction to choose. Okay, so that explains this condition here that you want this gradient of f when you take the inner product with respect to your d has to be negative. So that is a geometric explanation of what would be the feasible directions that you should consider. Now, among all the possible search directions, okay, so there are a lot of search directions that you can consider. There are lots of these that you can consider. By consider, I mean that they will satisfy this criteria that the gradient transpose d will be negative. Any d that can meet this criteria, they are allowed to be a good direction. But among them, you only want to pick one, okay, and then that one is called the steepest direction, okay. A lot of gradients, but there's only one that's called the steepest direction. Now, what do I mean? Well, let's say this is negative, okay? And among all these negative directions, let's pick the one that has the most negative value. Does that make sense? Okay, so let's go back by one picture. All these red arrows, they can give you negative value when you try to take this inner product. All these red arrows, they are allowed. But you want to find one such that this number is as negative as possible. Why do you want to make it as negative as possible? One more slide back. You go to here. Originally, you want it at optimum point. This is always positive. But if it is not optimum yet, of course you want your current value, okay, your current value x of t, to be as much negative as possible compared to your next point. So the next point has to be a lot lower, as low as possible. That's why, when you are going to here, you want to find a search direction such that, by picking the right d, this number is as negative as possible. Now, how can you make that happen? You don't even need to go through the math. You can tell me which direction would be as negative as possible. Would it be here, 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 or here? Okay? It has to be opposite to your gradient, right? Because if you're opposite to the gradient, then when you take the inner products, this will give you minus gradient f at x. That will give you the most negative value that you can think of. Okay? So, that goes to the steepest descent direction. What do we want to solve? Well, let's just try to minimize this objective function. So you have the gradient evaluated at x of t. You transpose with d. That's your objective function. You want to find a d. That means you want to minimize this. You want to make it as negative as possible. Okay, so you have this arc mean by minimizing this inner product. And then the solution will give you d of t. That will be your search direction. But I also have a constraint here. Why do I have a constraint that the magnitude of d has to be equal to the delta? That's also clear because look at this. Okay, so if you don't put a constraint here, then that means any search direction, okay, along the search direction, any number will work. So you can just scale it infinitely bigger. And so if you're a more algebraic person, you realize that this is unbounded below. Okay, so if you find a d, I can always scale the d by 1,000,000. That can make my cost value even lower, right? It's just a straight line, so you can keep going down without bound. So you need to bound the solution, and therefore you put a bound here, and the 2 norm of d is equal to delta. So pictorially, what it means is the following. you have this contour, and then you have a current point. That is your gradient. And then these are all the allowed search directions. And then now you're picking a search direction that's pointing to the negative side of your gradient. In addition, you also draw a circle surrounding your point, and that limits the magnitude of your search direction. Otherwise, your search direction will just go, it will just go to here. And that's not, this is the same, it's still a good search direction, but it's just, you have a step size to counteract that, right? Question here?
Oh yeah, so I was just going to ask, why would we need to control the delta D magnitude if we have the step size to control it?
Okay, so let's go back to here, okay? Once you choose the delta D here, in fact, the solution, you can show that the solution doesn't really depend on the D, okay? What you can do is that you can show that the D is actually arbitrary. And what you can do is that you can just choose this D to be maybe 1. Okay, that's your choice. Okay, and normally what you do is that you just choose this D delta to be 1, and then so that when you choose your search direction, it will be normalized. It will be a normalized direction. Okay, and then when you have the step size, you will control your step size over there. Okay, so this D, when you solve for the solution, you can show that this D doesn't really show up in your solution. All right, so here is the overall picture, okay? So you have a point, and then you have a gradient direction, and then you have all these feasible directions. You want to pick the one that is just opposite to the gradient, that is called the negative gradient. That's also called the steepest descent direction. And then you want to put a ball here so that everything is bounded. Then you get a good search direction. So that's the first part of the gradient descent. That explains why do we want to do an algorithm like this, okay? It is your current point plus a negative gradient, and then you have a step size. Okay, now, the second part of the gradient descent is, of course, the step size. So here you have an alpha of t. Alpha of t is called the step size. Now, if you don't choose the step size properly, of course you will overshoot, or if you choose those too small, it will take you forever to get to your minimum point. Okay? So in the literature, there are many ways of defining the step size. One is called the fixed step size, where you really fix, you just choose a constant. Okay? And then you try a few times and you realize that my step size is too big or too small, and then you adjust there. A more principled approach is called the exact line search method. What it means is that, let's say you are here, okay, and then let's say you're at this point, and then you find a search direction to be that will be a search direction, okay. Then along this trajectory, you are going to pick a step size that is as small as you want to pick a step size such that your objective value is as low as possible. So now when you go to this point, this is not necessarily the minimum point, because when you're here, you may still want to travel further. Okay? But if you write a cross section of this line, then you can see that that will give you a one-dimensional curve. Sometimes it will be like this, but sometimes you will also have another bump here, maybe another bump here. So it depends on where you are at. And then you start with 0, and then you try to search along the search direction, and then you want to pick a step size such that you will hit the minimum. Okay, so now correspondingly, the optimization problem will be this. You have an F here, and then your current point, and then your D is already chosen according to your steepest descent direction. And then you're trying to find an alpha, and you want to minimize this function by finding a good alpha. Okay, so that's called the line search algorithm. So within the gradient descent itself, it is an optimization algorithm. It's iterative. Inside, sometimes there is a thing called the line search algorithm. So within the optimization algorithm, there is another optimization step. You can show the following example. If you choose the objective function to be this quadratic equation, there is an exact form of this line search problem, which says that when f is 1/2 of the Hessian, and then you have the linear term, then the alpha, your optimum step size, will be given by this expression. Now, this may not hold in general for problems that are not quadratic, but for quadratic, you usually have this expression. There are also a line of research called the inexact line search. Inexact line search says that, look, this optimization problem could be extremely difficult because my F could be a deep neural network, and so it could be highly nonlinear. So I may not be able to find your alpha. And so you have inexact line search methods to approximately find a good alpha. Question?
So for the exact line search, if we choose the step size as that, then should it be just like that one iteration can optimize?
So the question is, if I run this exact line search, would I be able to get to my ground truth solution at one point? No. So let me draw you a problem like this. Okay. So let's say you are here. Okay, now you're finding the steepest direction. The steepest descent direction says that you want to go to here. Okay, and then according to your line search, you will go. That would be your x of 2. So when you're x of 2, are you there yet? Not yet, because you also want to find another steepest descent direction, which will be along here. Right? And then you go to here, and then you want to find another step size, which will say that you'll go to here. So that shows you need to have at least several iterations. That this step size does not replace the algorithm. Okay? It is one part of the gradient descent algorithm.
What is the intuition behind selecting the objective function?
Can you repeat again? I'm sorry.
What is the intuition behind selecting the objective function as f of xt?
Okay, so are you asking about this equation here? Okay, so the question is, well, can we explain this equation again? All right. So here is your current x of t. Here is your descent direction. Okay, so these two are given to you. That means what? What that means in this diagram, this is my x of t. This is already fixed. And then my search direction says it is d of t, so I have already also picked that direction, okay? And then I'm traveling along this direction. I want to pick an alpha such that along this contour, my objective value will be minimized. So this contour is the objective value defined by this f, all right? So you cannot go arbitrary. This f cannot be arbitrary. This f has to be the objective function that you try to minimize. And therefore, you want to find an alpha that can minimize this term. All right? Okay, so these are the two essential steps of gradient descent, the search direction and also the step size. Now, people have, of course, seen gradient descent being applied to many situations. Here, I just want to comment on why it works. Okay, here's the convergence proof. It's actually not a proof. It's a statement from this theorem, chapter 3.3 from this book of chapter 3. So what people have shown is that when you have a global minimum, so let's say your objective function really have a global minimum, and also assume that your function f is twice differentiable, and also it has certain kind of eigenvalue structure of your second order derivative, then you can show that the gradient descent will converge. Now, if you apply your gradient descent to any loss function, and if it doesn't converge, you cannot complain about the theorem here, okay? The theorem here has very strong assumptions to claim that the gradient descent works. What are the assumptions? Let me state again. One is that your function actually has a global minimum. Now, not all functions have global minimum. Let's say you're just minimizing a straight line that is unbounded below. So it's not guaranteed, right? So first of all, you need to assume that your x star exists, and then your function has to be twice differentiable. That's also very strong. And lots of these deep neural networks, when you have a ReLU functions, is not twice differentiable, okay? So you have some issue here. And you also need to assume that your second order derivative exists and is bounded by these two quantities, okay? So you have a Hessian matrix. The Hessian matrix has to have certain eigenvalues well controlled. That's also sometimes not easy to satisfy. And third, don't forget that you need to run this algorithm with exact line search, then you can get guaranteed convergence. All right? So if you have a problem in your hand, you run gradient descent, it doesn't converge, it goes somewhere else, and you say, okay, is there something wrong with my algorithm? It could be something wrong with the problem that you're encountering, and then you're using a method that may not be able to solve that problem. Okay? Just be aware that whenever you have an algorithm, although an algorithm may have a convergence guarantee, but when you look at the problem, the problem has conditions where your convergence guarantee may not satisfy. Right? Be aware of these issues. Now, there are multiple ways of doing this proof, but I will just draw a very, very simple picture to explain how this proof works. Okay, so the convergence of the gradient descent can be understood using a concept called the successive approximation. Essentially what it says is this: you have a function f, and then at every point, what you can do is that you can draw a quadratic function to approximate that curvature. So why? Well, let's look at this Taylor expansion. So you have f of x of t. Now I'm absorbing the epsilon, okay? So we have a d here, and then you can do a Taylor approximation to write into this form. And then the second order term will have 1 over 2 alpha. Now this alpha is magical, okay? It's actually capturing curvature of your approximation. Now you can make the alpha bigger, you can make the alpha smaller. If you make the alpha bigger, it will become flatter. You make the alpha smaller, it will become narrower. So you can choose your alpha. The magical thing here is that if you minimize this function with respect to your d, you can actually show that the d is minus alpha times this gradient. That's just another way of proving the gradient descent. So if you have this perspective, then you realize that what you should do is that here you have a function blue curve, okay? This is your blue curve function, and then you're drawing a quadratic function to approximate this blue curve. Then you try to select the appropriate curvature so that you can approximate this blue curve, okay? So then when you go there, you find a minimum point dt, and then you draw this curvature again, and then you go there. And so, if this function is convex, okay, it has certain Hessian matrix properties satisfied, and then you do a proper line search. Line search says that I'm finding the right curvature so that I can do the right approximation. And then, of course, by looking at this diagram, you feel that it is converging to the minimum point. Now, I'm hand waving here, okay? You feel that it's converging to the optimum point. In fact, the actual proof of the convergence follows this kind of logic. Okay, all right. So this slide is just to convince you that this gradient descent has multiple pictures. One, to show you why it is the right direction to go. Two, why it is the right step size. And three, why it works. Okay. Now, of course, behind all this, you have tons of proofs, tons of algorithms, variations around that. But that's the basic three components of the gradient descent. I hope you can get that. Is it okay? All right, so there are a couple advices on gradient descent, which you can read it by yourself. I just want to comment that the gradient descent is so widely adopted because it is a first-order method. It doesn't require second-order idea of your function. And first-order information is usually okay to obtain. Even in the deep neural networks, we know that they have backpropagation steps, so you can get the gradient information reasonably easy. Okay. Now, in this course, I won't ask you to write your own gradient descent algorithm. Okay. However, I will want you to, whenever I ask you to solve an optimization problem, I ask you to use a CVX, an optimization package, so that you can get to the solution rather than spending time debugging your optimization algorithm. Okay. When you try to implement your gradient descent by yourself, there are a lot of small, tiny bumps that you will hit into. For example, whenever you have a nonlinear function, you may not be differentiable, and so how can you guarantee convergence? Stuff like that you need to worry about. Okay. So today, the libraries that you use in deep neural networks, they are well written in such a form that the gradient descent usually works. Okay, but when you try to write everything from scratch, it may not be as easy. Okay, any questions so far? Yes.
The previous slide, so you're trying to go on. Yeah. So for this one, are you iterating the D or are you iterating the X to find an optimal solution? That's what you're looking for.
Okay, so the question is, in this diagram, am I iterating with respect to D or am I iterating with respect to X? It is iterating with respect to X. Okay, so let me explain. So currently you're XFT, and then you solve this approximation, you find a right dt, and then you move your x of t to x of t plus 1 according to the dt. So you go there, right? So you go from x of t, go to x of t plus 1, and then at x of t plus 1, you write a new approximation, and then you find a new d plus 1, and then you go there. So the iteration is always on x of t. So the dt is like a byproduct. So if you actually go back to the original gradient descent diagram, here you're also finding the dt at every step, right? Because so is the dt the solution I'm finding? No, you're not finding the dt, but you need to find the dt in order to find your x of t plus 1. So that's the same story here.